this video, I'm going to guide you through one of the possible ways of deriving the Lorentz transformation. Now, since you are watching this tutorial, you probably know that the transformation is the central part of Einstein's relativity, and you may wonder why it is called Lorentz transformation and not Einstein's transformation, or why it is called Einstein's relativity and not Lorentz relativity. The reason is that in 1895, 10 years before Einstein's relativity, Hendrik Lorentz accidentally obtained the transformation that holds his name when he was trying to reconcile classical physics with the results of the Michelson-Morley's experiment. I say accidentally because not only did he assume the existence of some ether, a medium of propagation for light, which we nowadays know it doesn't exist, but also because he supported the concept of absolute space and time and misinterpreted the meaning of the transformation. In addition, his theory was still assuming Newton's mechanics to be exact, which we know is not the case. What Einstein did was revolutionary, in addition to being simpler. He dropped the concept of ether and absolute space and time, adopting the concept of relative space and time, and showed that the Lorentz transformation could be easily obtained from two postulates. The first postulate is Galileo's principle of relativity. The laws of physics are the same in all inertial reference frames. This postulate is directly supported by experiments. Just think about it. When you are cruising in a commercial flight and there are no turbulences, the flight attendant can pour coffee into your cup in exactly the same manner as when you are on the ground, because in the frame of the plane, when it flies at constant velocity with respect to the ground, the laws of physics are the same as on the ground. The second postulate is from Einstein and states that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. This postulate is certainly very counterintuitive, but it is directly supported by the result of Michelson-Morley's experiment. It is also supported by Maxwell's theory of electromagnetism that predicts a constant speed of light without ever referring to any reference frame. Deriving the Lorentz transformation requires no more than 8th grade mathematics, and the two starting postulates have never been faulted by any experiment. Thus, all anti-relativists who claim that the Lorentz transformation is wrong are just making up results that they take as facts. Doing so is by definition pseudoscience and is therefore totally worthless. So, we are going to consider two inertial frames f and f prime, where f prime is moving with some constant velocity v with respect to f. Each frame has its own set of axes and its own clock, and we are going to choose the x and x prime axes to be parallel to the velocity v. Without any loss of generality, we can always choose the origins O and O prime of the axes to match at a certain time, and the two clocks can be synchronized when this happens. So, in the following, we are going to take the frame F to be our frame of reference in which we are at rest, and F prime is therefore moving at velocity v. But it is important to note that the situation is perfectly symmetrical and that we can as well say that the frame F is moving with velocity negative v with respect to F prime. Consider now an event M that happens at time t and coordinates x, y, z in the frame F. The purpose of the Lorentz transformation is to determine the space and time coordinates t prime, x prime, y prime, z prime of that same event as seen from the frame f prime. There is a step in the derivation of the Lorentz transformation that is often overlooked. It consists of determining how lengths that are perpendicular to the velocity change when going from f to f prime. So let us do it properly. Suppose that there is a blue stick in f prime that is perpendicular to the velocity and it has a blue marker attached to the top. Before the stick was in motion, its height h at rest was measured on a paper sheet that remains in F. When F' and the stick pass in front of F and the sheet, the marker makes a mark indicating how the stick's height is perceived from F and compared with its recorded height at rest. There are three possibilities. The mark can be below h, at the same height, or above. But there is also an identical stick, but red, with a red marker in F and a sheet in F', so that a red mark indicates how the red stick's height is perceived from F'. So, let us analyze the situation from the point of view of F. As we mentioned, there are three possibilities. If the blue mark on F's paper is below h, then it implies that the blue marker is below the red marker, since the red marker in F is at height h. So, the red mark on F's paper must be above h. On the contrary, if the blue mark is above h, then the red mark must be below h. And if the blue mark is on h, then the red mark must also be on h. We can as well analyze the situation from the point of view of F'. If the red mark is below h, then it implies that the blue mark must be above h. If the red mark is above h, then the blue mark must be below h. And if the red mark is on h, then the blue mark must be on h. However, the outcome of the experiment must be symmetrical, since the experiment itself is symmetrical. This means that if nature chooses the first outcome in F, then it must also choose the first outcome in F', or it must choose the second outcome for both frames, or the third one. So let us look at the first possibility. We have the blue mark below h, and we must have at the same time the blue mark above h. This leads to a contradiction, so it can't be correct. So let us look at the second outcome. A similar thing happens. The blue mark should be above h, and it should also be below h at the same time. Again, a contradiction. This leaves us only with the last possibility. And this time there is no contradiction. All the marks are on h. The conclusion is that measurements of lengths that are perpendicular to the velocity give the same results in F and F'. In other words, the coordinate transformation for the y and z direction is trivial. Y' equals y and z' equals z. In order to determine how the remaining t and x coordinate transform, we can make use of an imaginary light clock. In such a clock, the ticking time is determined by the time it takes for a light pulse to perform a round trip between two parallel mirrors. If we call d the distance between the two mirrors, then we can determine the ticking time. Remember Einstein's postulate. The speed of light is a constant c for all observers. Speed, by definition, is the distance traveled divided by the time of travel. So we conclude that the ticking time is t equals 2d over c. Now, suppose the two frames F and F' have identical light clocks. They are oriented in such a way that the mirrors are parallel to the direction of the velocity. The distance between the mirrors is therefore perpendicular to the motion and appears the same whether the clock is moving or not, as we have already proven. According to Einstein's postulate, the speed of the light pulse of the moving clock is equal to c, because it must be the same for all observers. However, it is clear that the light pulse travels a longer distance when going from the bottom mirror to the upper one, and vice versa. Thus, it takes a longer time to perform a round trip. We conclude that the moving clock is seen from F as ticking slower. Note that the light pulse of the moving clock remains all the time horizontally centered with respect to the mirrors. However, if we trace the path followed by the light pulse, we find that it follows a straight oblique line from the bottom mirror to the upper one. It also follows a similar oblique path, not represented, when going from the upper mirror to the bottom one. The fact that this path is straight and oblique is obvious, not only from this animation, but also from the fact that there can't be any vertical acceleration of the pulse, since there is no acceleration of the moving clock with respect to f. And the horizontal component is just the velocity of the moving clock, which we explicitly defined to be constant. The reason why I am making it clear in this video is that there is a guy on Quora, Ira Clark, who keeps flooding everyone's post with his fake science, claiming that the Lorentz transformation is wrong because the light pulse of the moving clock supposedly doesn't follow an oblique straight line when seen by an observer at rest. So don't fall for his pseudoscience. In order to make some calculations, we can take pictures of the mirrors when the pulse is at the bottom and when it is at the top. And this should strongly suggest that there is something important about that oblique line. So I'm going to invoke here the 8th grade math that I was referring to earlier, more precisely the Pythagorean theorem. Let us call capital D the length of the oblique line. This line rises by a height h, and the horizontal distance over which it runs is just the distance covered by the clock in half of its observed ticking time t. Hence, the horizontal distance is vt over 2. Once again, by definition of the speed, the ticking time is given by the round-trip distance divided by the speed of light. Thus, the ticking time t of the moving clock as seen from f is given by 2 times the oblique distance capital D over c, and the ticking time t prime of that same clock in its own frame f prime is given by 2 times the distance d between the mirrors over c. Now, the Pythagorean theorem tells us that capital D is the square root of the square of the horizontal distance vt over 2 plus the square of the distance between the mirrors. We can rearrange the ticking time equations to express capital D as ct over 2 and small d as ct prime over 2, and substitute these expressions into the Pythagorean theorem equation. This results in an equation that involves only times and velocities, no distances. We can simplify it by multiplying it by 2 and squaring it, and finally we can solve it for t, the time observed in f. We obtain the well-known time dilation formula. Dilation because the observed time will always be greater than the time measured in the frame where the clock is at rest, as long as the velocity v is non-zero. It is important here to mention that the time dilation formula applies only if the time t prime is a proper time, that is to say, a time between events that is measured in the frame where these events happen at the same location. Applying this formula to non-proper times is a common mistake that leads to many apparent paradoxes, such as the famous twin paradox. This is also a mistake that many anti-relativists are fond of, such as Pete Venter, who absolutely wants relativity to be wrong, no matter how many times you explain to him his obvious mistakes. But let us move on. We rotate now the clock by 90 degrees so that the light pulse now propagates in the direction parallel to the velocity v. The first thing to notice is that the moving clock is still at rest in its own reference frame f prime, and its ticking time t prime is unchanged. It is still a proper time, therefore the time dilation formula still applies, and the observed ticking time t in f is unchanged. However, the observed distance d between the mirrors is no longer perpendicular to the velocity, so there is nothing that says that it should be equal to d prime. Here we can see that the pulse in the moving clock is having a hard time to reach the front mirror, but when it is reflected, it reaches the back mirror very fast. So let us decompose the path followed by the pulse. We have the stage where the pulse propagates from the back mirror to the front mirror. Let us call t1 the time that it takes, as seen from F. During that time, the front mirror moved by a distance equal to vt1. Then we have a second stage where the pulse propagates from the front mirror to the back mirror. We call t2 the time that it takes, and during this time the back mirror moved by a distance vt2. Something that we know is that t1 plus t2 is the time for a round trip of the pulse, so it must be equal to the observed ticking time. Now the distance traveled by the pulse from the back mirror to the front mirror is d plus vt1. According to Einstein's postulate, this distance must be equal to ct1. So we can solve for the time t1 and find that it is equal to d over c minus v. Likewise, the distance traveled by the pulse from the front mirror to the back mirror is d minus vt2, and according to Einstein's postulate, this distance must be equal to ct2. We conclude that t2 is d over c plus v. So we can eliminate the times t1 and t2 by substituting their expressions into this formula. After simplifying, this gives us t equals 2cd over c squared minus v squared. And finally, we can totally eliminate the times by substituting them into the time dilation formula. We obtain a relationship between the observed distance d and the distance d prime between the mirrors when they are addressed. After simplifying, we finally obtain the length contraction formula. Contraction because the observed distance d will always be shorter than the distance between the mirrors when they are addressed, as long as the velocity is non-zero. As for the time dilation formula, it is important to note that the length contraction formula applies only if the length d prime is a proper length, that is to say, a length measured in the frame where the objects are addressed. In addition, the length must be parallel to the velocity v for the contraction formula to apply. Again, a common mistake is to apply the formula to a length of an object that is moving. Since time dilation and length contraction apply only to proper times and proper lengths, we still need to figure out how the coordinates x and t of any event transform when going to the moving frame f prime. For this, let us consider an event m that happens at coordinates t, x, y, z in f and t prime, x prime, y prime, z prime in f prime, and consider the situation as seen from f. From this point of view, it is f prime that is moving at velocity v. We can make use of Castle's relation. Vector OM equals vector OO prime plus vector O prime m. In f, the vector OM has coordinates xyz, and the vector OO prime has coordinates vt 0, 0. What are the coordinates of the vector O prime m? This vector in f prime has coordinates x prime, y prime, z prime by definition. But we already know that y prime equals y and z prime equals z. And we also know that x prime is a proper length because the x prime axis is addressed in f prime. So we conclude that in f, this x prime coordinate is contracted. By plugging these vectors into Castle's relation, we obtain this relationship between x and x prime. Solving for x prime, we obtain the formula that gives the coordinate x prime as a function of the coordinates from f. The last thing we need to do is to figure out the formula for the time coordinate. To this end, let us consider now the situation as seen from f prime. In this frame, f appears to be moving at velocity negative v. The vector O prime m has coordinates x prime, y prime, z prime. The vector OO prime has coordinates vt prime 0, 0. and we know that the vector OM has coordinates xyz in F. Again, we already know that y prime equals y and z prime equals z, and we also know that x is a proper length because the x-axis is addressed in F. So we conclude that in F prime, this x-coordinate is contracted. As before, we can plug these vectors into Castle's relation, and we obtain this relationship that we can solve for x prime. So we have now two expressions for x prime that we can equate. Doing so leads to an expression in which t prime is the only primed variable. Solving for t prime, we obtain the formula that gives the coordinate t prime as a function of the coordinates from F. We have now the complete Lorentz transformation for the case where the relative motion of the frames F and F prime is parallel to the x-axis. It is now easy to generalize it to any direction for the velocity. For this, all we need is to realize that we can always decompose the position vector r of the event in F as a component that is parallel to the velocity plus a component that is perpendicular to it. As we have shown, the perpendicular component is unchanged when going to F prime, and the parallel component transforms exactly as we just showed in the particular case where the velocity was parallel to the x-axis. So we can condense the transformation of the four coordinates into the two equations that are shown. Finally, it is common to define the Lorentz factor gamma v as 1 over the square root of 1 minus v squared over c squared, which allows us to simplify the writing of the Lorentz transformation. It is important to keep in mind that the Lorentz transformation is between inertial frames, and because of this, some people wrongly believe that special relativity cannot treat accelerated reference frames and that general relativity is required for such a case. This is not true. Special relativity is perfectly capable of dealing with accelerated reference frames. For a concrete example, watch my tutorial on how to solve the twin paradox.